I want to thank the organizers for the invitation. I've really enjoyed the conference. It's good to see all the research that is going on within the SEC universities. It's been very enlightening. I'm very happy to go after Mark and Lonnie, because I'm going to use some of their material in my presentation, so it's very nice to do that. The title of the presentation is Integrating Biofuels Production to Wastewater Generation and Treatment. Before I start, I want to do some acknowledgements. I want to acknowledge my dear colleague, Dr. Todd French, and the other staff members in Mississippi State University. Dr. Todd French, we've been working together for many years, and all the research that I'm going to present here, we've been working together on it. And like one of the previous speakers mentioned, the staff members and the students are the one doing the hard work, and most of them are here today. I also want to thank our funding organizations over the year: General Atomics, the Department of Energy, Environmental Protection Agency, the National Science Foundation. I teach a biofuels class in Mississippi State University. Been doing that for the last year and a half. And I started the class with this statement. And you all know the 1.3 billion ton study that the Department of Energy did a few years back, and they updated it, I think. And if we take that study and take the energy content of that 1.3 billion tons of biomass, and in addition to that, we take what we consume in petroleum, and take the energy content of that, we come up with a displacement potential for biomass. And that displacement potential is about 60%. Now, what does that number mean? That's the maximum displacement we can get if we operate everything at 100% efficiency. And that is not the case. Many of the technologies that we've been discussing here over the last year and a half, the efficiencies are probably below 50%. Some of them are pretty close to 30 or 20%. The message from that is that if we want to displace the most petroleum that we can, we have to take advantage of a lot of synergies. We have to integrate different technologies. We have to be close to the biomass source. We have to take advantage of the infrastructure that we already have in place in order to displace as much petroleum as we can. I'm going to talk about biodiesel a little bit. The renewable fuel standard was mentioned yesterday, and there was an article in Biofuel Digest about a week ago, basically saying that the Environmental Protection Agency is going to consider using biodiesel to meet the quota that cellulosic ethanol is not meeting in the renewable fuel standard. And they're implying that there's going to be a very large increase in biodiesel demand over the next 2 years, 2014 and 2015. Biodiesel, I'm not going to go through all the bullets here. It blends very well with petroleum diesel, has very good lubricity. It has a lot of capacity in place already, especially in Europe. So it's a very well-established fuel. If we're going to get another increase in the demand of biodiesel, we need to find cheap sources of oil that are not competing with the food market. If we don't want what happened several years back with soybean oil prices to happen again. We've been discussing this over several presentations. The problem with many of the biofuels that we discuss here is feedstock. Feedstock. We need cheap feedstocks in order to be able to produce biofuels at competitive prices with petroleum. We don't want to compete with food. So that's another requirement for these feedstocks that we want to produce or use for biofuel production. Some alternatives, non-edible oil sources, waste cooking oils, and sewage sludges, and I'm going to focus on this one today. Mark Hofstapel mentioned wastewater. There are many, many wastewater treatment facilities in the U.S. We treat about 35 billion gallons per day of wastewater in the United States. That's municipal wastewater. That doesn't take into account industrial wastewater. These wastewater facilities, if they are using biotreatment, they generate a sludge. It's a mixed consortium. That sludge that these wastewater treatment facilities generate is a mixed consortium. And Mark mentioned the idea of using mixed consortium as robust microbial seeds for biofuel generation. In Mississippi State, when we started this research several years back, we went to a wastewater treatment facility and took these sludge straight from the wastewater treatment facility, went to the lab, dried it, extracted, produced biodiesel from it. And we realized that from that sludge, we were able to produce between 3% and 7% biodiesel. That's about a gallon of biodiesel. The 7% level, it's about a gallon of biodiesel per 100 pounds of dry sludge. When we did the economics of that, we realized very quickly that if we wanted to produce biodiesel from that material, which is a waste that is wasted every day in wastewater treatment facilities, we had to increase the oil content of that sludge. Now, what we discovered was that we could do that by increasing the carbon-nitrogen ratio at which these microorganisms grow. In wastewater treatment facilities, the mixed consortium grows under a very low carbon-nitrogen ratio. They are carbon deficient. If we increase the carbon in the wastewater and grow them with a high carbon-nitrogen ratio, we were able to increase the lipid content. That lipid that I mentioned there is oil, very similar to a vegetable oil or an animal fat, up to 35%. The economic estimates that we've done in Mississippi State University, we can get a lipid, we call it biocrude, at about $2.15 per gallon, and you can add about 30 to 60 cents per gallon to produce the biodiesel. So it's a biodiesel at less than $3 a gallon. Now, this is a wastewater treatment facility here, and in a conventional wastewater treatment facility, they take this sludge, they dry it. This is a drying and belt press in a wastewater treatment facility. Actually, we went to Puerto Rico last week to visit a wastewater treatment facility. So these pictures are from a wastewater treatment facility in Puerto Rico. And after they dry it in Puerto Rico, this is a pile of sludge right there. Lots of microorganisms in there. What are they doing with that? They are composting it. They are basically making a soil amendment, and they sell it at about $12 per cubic yard. Now, we want to use that in a different way. We want to take the microorganisms in there and convert those microorganisms into a mixture that can accumulate oil that we can use for biodiesel production. Very interestingly, in Puerto Rico, there is a law that they cannot take biomass to landfills because they are limited in terms of landfill space. What I'm not showing here is that they have a 1-year inventory of biomass in the back of this building. It's a huge pile of wood. They are using that to blend it with the sludge for the composting process. We want to use it in a different way. And you'll see that how we want to use it in a few slides. The principle or the mechanism by which these microorganisms accumulate oil, it's the mechanism that oleaginous microorganisms use to accumulate oil. Very similar to all of us here. They have been feeding us very well in the conference, and we have been eating a lot of carbon. If we eat a lot of carbon, what these these microorganisms, what they do at a very high carbon-nitrogen ratio, you can see the glucose here, and the nutrients when they go way down, at a very high carbon-nitrogen ratio, they accumulate oil. These globules inside the microorganisms, those are lipids, and these lipids, very similar in composition to a vegetable oil or an animal fat, they can be used to produce biodiesel. So very similar to us, eat a lot of candy, no exercise, we get fat. These microorganisms are getting fat too. And you can see the fatty acid profile here. This is the recycle activated sludge. And when we start increasing the carbon-nitrogen ratio, you can see how the fatty acid methyl esters, or the saponifiable lipids in this case, increase significantly. The C18-1 is the one that is increasing the most, and that's an indication for these oleaginous microorganisms. Most of the oil in these oleaginous microorganisms, the profile is in that C18-1 range. We did studies with the Environmental Protection Agency, did experiments in the lab, collect the samples in the lab, send the samples to the Environmental Protection Agency in Cincinnati, and they did DNA sequencing, and they did microbial ecology experiments, and we very quickly realized that the microbial diversity of the microorganisms in the mixture was reduced significantly as we increased the carbon-nitrogen ratio, indicating that the microorganisms that are in there after we increase the carbon-nitrogen ratio, the predominant ones are ones that are accumulating compounds for energy purposes. We did this not only for one wastewater treatment facility, but we did it for several. And that make us feel very confident that it doesn't matter where the sludge is coming from a municipal wastewater treatment facility, if they have secondary treatment, if they are generating secondary sludge, we can take that sludge and convert that sludge into an oily sludge or a sludge with biocrude that we can use for biodiesel production. This would be the concept. This is the traditional wastewater treatment facility up here. Now, in our case, we would take a tank that we are classifying it or labeling it as lipid accumulation chamber. That tank, we would take primary wastewater. We would take the sludge into that tank, the secondary sludge. We would supplement that with sugars from lignocellulose. And remember that I told you in Puerto Rico they have a 1-year inventory of wood. In that particular case, this works very well because the wood is right there, and it could be converted to sugars to produce oils for biodiesel production. There are several other cases where this synergy works very well too, and I'm going to mention one more in a few slides. Lonnie covered this very well, so I'm not going to mention too many details about this, but the lignocellulose can be converted into sugars, C5, C6 sugars, and other things. And conventionally, you can produce ethanol, but in our case, we want to produce lipids for biodiesel or renewable diesel. This is our pilot facility in Mississippi State. We have about 800 liters of fermentation capacity with all the ancillary equipment to produce or to collect the microorganisms, to dry, to extract, to recover the solvent. So many of the experiments that we are doing that at this level. This is kind of what we want to do now. Collect biomass, mix that biomass with wastewaters from industry or from municipalities. We are very interested in pulp and paper wastewaters because they already have a lot of carbon in there. That's another synergy that I was mentioning before. In addition to that, they collect the biomass for you. And the biomass is coming in every day. So there's a very good synergy between the pulp and paper industry, like Lonnie mentioned, biomass collection, and in our case, we would take their wastewater, we would mix their wastewater with a microbial seed from a wastewater treatment facility, produce oil, and then we can take that oil and produce either renewable diesel, send it to a refinery to produce renewable diesel. And in the United States, ConocoPhillips had the beginnings of converting lipids into biodiesel, into renewable diesel. They don't do that anymore. But Valero in Louisiana and Neste Oil in Europe are doing that, or we can go with the conventional biodiesel production process. This is for the pulp and paper industry. Take pulp and paper, wastewater from different places within the pulp and paper facility. What I'm showing here is biomass, and this hydrolysate was prepared by Lonnie's process. This is a hydrolysate prepared with the phosphoric acid process prepared by Lonnie, sent to Mississippi State University. We're very thankful for that. We did the fermentation process, and you can see here that with the sludge coming from wastewater treatment facilities, the microorganisms here accumulated, I don't know if you can see it clearly, but it's about 25% lipids. Now, the lipids, based on that data and based on the wastewater that is produced within that particular wastewater pulp and paper facility in Vicksburg, Mississippi, International Paper, and based on the carbon that they can produce, there are many synergies in here because within the pulp and paper industry, there are sawmills very close by. There is cardboard waste that they generate that right now they sell for very cheap. There is bark also that is available. Based on that, we estimate that from that particular facility, we could produce about 15 million gallons of biodiesel. And the trucks are right there too. The trucks are right there to consume that biodiesel. And they're very interested in this technology. I want to show quickly cost here. And somebody mentioned before what the cost included in Mark's presentation. It includes everything we can find, going from labor to equipment to capital investment. You can see here that we can estimate a bio-crude per gallon of about 215. There are two things here that are very important. We're assuming a sugar cost per pound that is low. It's about 5 cents per pound. We understand that that is a low estimate. However, even if we increase that sugar cost to about 10 cents a pound, which is a target for the Department of Energy, this is going to still be under $3 a gallon. The reason that I'm putting this here is because I want to show you that ideation, it's a an issue that we have to work on in terms of reducing the cost of aeration, and the synergy to find biomass sources very close to where we need them. We still need to take a very close look at that, but with the pulp and paper industry, that's easier to do. Now, this is something that we just started about 6 months ago, and it's very similar to Mark's process, or the beginnings of Mark's process. We want to integrate anaerobic digestion with lipid accumulation. The reason we want to do that is because many wastewater treatment facilities already have anaerobic digesters. And we would like to change the way they are operating those anaerobic digesters so they change the operation to produce not all methane, but a mixture of methane and VFAs, or volatile fatty acids. The volatile fatty acids we can use for biocrude production. The methane we can use to power the aerators, which are energy-consuming unit operations. In the experiments that we have started in the lab, the microorganisms from the wastewater treatment facility can produce biocrude or the lipids using BFAs. So that's a sign that if we can take the biomass and produce BFAs from that biomass using anaerobic digestion at a high enough concentration, we would be able to integrate anaerobic digestion and lipid accumulation and maximize the efficiencies of the two processes. This is kind of a summary of the whole process. Again, we would take anaerobic digestion, produce volatile free fatty acids, take the volatile free fatty acids to the aerobic chamber, and in there produce or accumulate the lipids. The methane produced we would also use as an energy source within the process. Lonnie and Mark mentioned these, so I'm not going to go too much into this, but I think lipids or biofuels are really the low-hanging fruit here. I think, and I apologize for some of the symbols here, but I think that the real money, and I think Lonnie mentioned these, it's with the specialty chemicals. In addition to lipids, there are other chemicals that can be produced using microorganisms, and there are some synergies that I don't think we are taking advantage of. Pyrolysis generates a wastewater that could be used to produce other biofuels or lipids using microbial mixtures. And within the pyrolysis process, there are several chemicals that could be integrated with chemicals from biological processes to produce very useful materials. In addition to that, we can produce fuel additives to improve combustion processes. Conclusion. Integrating wastewater treatment and municipal solid waste could generate significant amounts of oil for biofuel production. Specifically, industrial operations generate waste and wastewater that could be converted into fuels and chemicals. Secondary sludge is an available and abundant microbial seeds to produce biofuels and chemicals. And the way we envision this is all this wastewater infrastructure that we have in the United States that needs updating. Many of these wastewater treatment facilities are 50 years old or more. We can envision the new or a new paradigm of treating wastewater, making the wastewater treatment facilities more efficient and generating biofuels from those type of wastewaters that could be used as transportation fuels. And anaerobic digestion and aerobic fermentation could be combined also to produce biodiesel. I think that's it. That's all I have. I'll be glad to answer any questions.
Yeah, questions?
Hey, during Boulder, Louisiana State University, you mentioned that you increased the rate, carbon to nitrogen ratio to 70:1. Or
Yeah.
so what is the carbon source?
In that particular experiment, the carbon source was glucose. We tried different carbon-nitrogen ratios. We tried 10:1, 40:1, 70:1, 100:1. At one point, our staff members were really adding almost a thick syrup to the fermenters, and those were the experiments that we were doing. The carbon source, we want that carbon source to be obviously the lignocellulose. We want that carbon source to be wastewaters. There are several wastewaters. I mentioned the pulp and paper industry. There are several, I'm sorry, I have this here going through the slides. And there are several wastewaters. Pulp and paper is one of the industries. If you go to the pulp and paper industry, within the pulp and paper industry, there are several sources of wastewaters with very high carbon loadings. One of the wastewaters that we consider from the international paper in Mississippi was 65,000 milligrams per liter, or 65 grams per liter. That's about what we use in the lab with glucose at the 70 or 40:1 ratio. Another company that we're looking at in Mississippi, they process used oils and they produce free fatty acids for the specialty chemical industry. Their wastewaters are also very high in carbon, so and they take glycerin from wastewater from biodiesel facilities too. We could use glycerin to increase the carbon content and produce the lipids too. So in terms of carbon sources in the lab, we obviously use glucose. We have used xylose. We have used real hydrolysates. We have used artificial hydrolysates. In application, we want to use lignocellulose hydrolysates or the carbon already in the wastewaters. Lonnie?
What kind of concentrations of lipids on grams per liter basis are you able to achieve in your system?
On grams per liter basis, Andrew, you will have to help me here if he's here. Andrew.
About 8 grams per liter roughly.
What, in grams per liter basis? Is
You said 8.
Is it 8? 8 grams per liter?
How do you go about recovering that economically?
We have, that's a good question, Lonnie, thank you. We are doing several things in terms of separation processes. You know, when you look at this picture here, you see the sugars coming in and the wastewater and the biofuels going out, but in the middle there's a lot of research in terms of catalysis, separation processes, and many other things. One of the processes that we are using is supercritical methanol. With supercritical methanol, it's a way of producing biodiesel. You don't need a catalyst with supercritical methanol. It's very tolerant to water, so the idea is to not dry the mixture coming out of the fermenter and just use supercritical methanol to produce the biodiesel. There's also in situ transesterification. We've done several studies using in situ transesterification where you dry, but we've discovered that you don't have to dry to the 95% solids. You can dry to the 50% solids and then add to that mixture the reactants that you would use for biodiesel production, and you can produce a biodiesel in one pot. It would be a one separation reaction system. So we are trying several technologies to take the microorganisms as they are without drying them, and then lyse them in the process of producing the fuel.
Thank you, Rafael.
Thank you.